Okay, this morning we are going to talk about operational amplifiers. And before we do that, we need to get the concept of impedance very clearly. So what you see on the screen is are three of the most elementary elements that we use in electrical systems. And combinations of these also build circuits that do certain things. So the first we're going to do is we are going to look at the equations of each one of these elements. So let me disappear from here, and we'll concentrate over here. As you can see, we have a resistor here. This was the resistor. How is the equation of this? If you have the current that circulates through it, the voltage across this element is really I times R, right? Very good. And you can say that if you put this form in here, you could say that resistance is B over R divided by I, right? This is called the voltage. Let's do it for the next element. The voltage across the capacitor. Isn't it true that this is 1 over C, the integral of I dt, right? Okay. And if we have this voltage across the inductor in here, this is equal to I L, this is, let's see, C, and then we have L in here. This is L times di dt. Okay, so in here this R is the form of the impedance. We're going to call it Z. So Z is like R in here. Z, the impedance. So this call it the resistance here. Resistance form, and then the impedance form. Okay. If you apply the Laplace transform to this, obviously B of S is equal to R times I of S. Yeah. If you do it over here, you can say that the voltage C of S is equal to 1 over C times 1 over S, right? Times I of S. So this element, like here, do you notice that is like this, see? So you could say that voltage on the capacitor is equal to the impedance times the current, like this. Let's call it where the impedance is 1 over CS. Okay. Now for the inductor, if you put the voltage in the S domain, this is L times S times I of S, right? So you could say, do you notice here again this form? Do you see? This form like this is like this form, and it is like this form, where you can say that that the voltage across the inductor in this case is the impedance across the inductor times the current. So the impedance across the inductor is going to be L times S. So this is just a different form of writing the equations of the three elements, but all the three elements follow the same format as this original equation. So in the case of the resistor, R is equal to Z. So Z is the impedance. So Z of R is R. But if you look and you apply the Laplace transform and you put it in the same form, look, this is what you'll have, Z of C. But if you do the same thing for the I element, you will have this. So we could conclude, and maybe I'll circle with another color in here, about the concept of the impedance. For the resistor, the impedance is this. For the capacitor, this is the impedance right here. And for the inductor, this is the impedance right here. Okay, very good. With this introduction, basically what I have done is to set you up to understand a little bit of the operational amplifiers. So let's just draw one of them. One of them is called inverting operational amplifier. Okay. Okay. So let's draw this operational amplifier, and we are going to use this concepts of impedance that we just talked about. So in here we're going to say that you have a resistor here, and in here you have a also a resistor like this, and then down here you have an operational amplifier that is actually looks like this. Okay, and this is the little device that is of our interest today. Okay, this is your operational amplifier. Now the way it works, we need to explore this before we understand this a little bit more. This is the so-called inverting operational amplifier. Inverting operational amplifier, yeah? Let's talk about this. In here, what happens is that you have an input voltage, let's call it voltage input in the S domain. You, of course, on this one you have Z, which we're going to call it Z1 of S, like this. And you know, from the concept upstairs, that the resistance is Zn for a resistor here. This is going to be Z sub 2, like that. And this operational amplifier, we need to explain how this thing actually works. So if you have in here, the way this is designed is in such a way that the current that goes through this, call it, the current in here is always 0. This is the way it is defined. So in here you have a current that circulates like this, and this is going to be, let's call it I sub 2, and on this side you have the current like this. We are going to call it I sub 1, right? I sub 1 of S, and the one here, I sub A, is 0. So this is I2 of S, like this. And in here you have, just to make sure we understand, this would be I1 of S. The property of this device here, since this is 0, it's obvious that at that point we will have to add the voltages and see add the currents. This is the output voltage, okay, output voltage. Yeah, so here's our problem and our challenge. First of all, what does this element do? You know, what does it do? How is this actually used? You have an input voltage here, you have a current 0 there, you know, here you have the output voltage over here. If this current is 0 here, something happens on this little circuit, and that little circuit does something to the input voltage here. What is that? I think that's what we need to address. So if you take a look at just the operational amplifier, just the operational amplifier. So why don't we just put a little you know, you could say details. Of the op amp. For the short, people call it op amp, like that. So if you have this in here, we are going to, let's say, draw it like this. What is really going on inside this little funny symbol that has the triangle in there? If you have the voltage here, and out here you have this reference point, this is your plus and minus, and then it's like this. This is the output voltage. So what does it do? The first thing is, basically, we can look at this element as a transformer. You have a voltage here, and then you do something to the voltage, and then you get a voltage out. But you see, this is not really a true transformer, because this element is not like a power conserving element and is passive. No. Inside of this, it has an external power source. It has like it has a voltage. Okay, this is like a voltage, the negative side, and a voltage on the positive side. So this is basically power device. Let me just put it in. That's what makes the difference. This is a power device. Okay. And what does it do? Let's just look at 4 characteristics of this. Let's see, number 1. The input voltage that we have in here is like V sub 2, or this is V sub 2 here. That V sub 1 minus V sub 2 is the differential input. This is the input to this. Okay? The second characteristic of this thing is that it has a high input impedance. High input impedance. So this term, like the resistance, is high. 3 has a and the 3 has a low output impedance. Okay, and 4, it has a high gain. So this A in ideal operational amplifiers is close to infinity, and therefore what you have in here is that the output voltage here, the output is equal to this constant, this operational amplifier constant, times the difference between the 2 voltages. So basically this is called a powered operational amplifier. The way I have it on the right hand side is simply an element that takes this voltage and looks at the difference between the voltage and produces an output voltage. So this is basically a powered transformer, not a conserving passive transformer. So let's analyze a little later now the circuit that we have on the left hand side. So we'll stop for now, but we'll continue with